Hello everyone. Today we're going to be answering a very simple question: why are black holes black? And the reason is probably not what you're used to being told. Most people are often told that it's because nothing, not even light, can escape from a black hole, because the curvature of space-time is so great at the horizon. This is really not the reason. Firstly, it's not even true that the curvature of space-time is large at the horizon. And secondly, we don't ever see anything fall past the horizon. And so we should see everything that ever fell into it pile up there. But instead, we actually see nothing but darkness. Let's now dive a little bit deeper to find the real reason why black holes are black. Firstly, what actually is a black hole? In theoretical physics, the simplest black hole, known as the Schwarzschild black hole, is a solution to Einstein's field equations in general relativity. Schematically, they say on the left-hand side that space-time curvature, which is really the origin of gravity, comes about or is sourced by energy and momentum, the right-hand side of the equation. Importantly, there can still be space-time curvature even in a region where there's no energy and momentum there. All that matters is that there's some energy and momentum somewhere else in the universe that is sourcing this space-time curvature. The metric tensor describes the geometry of the space in which you inhabit, and although it's got a really fancy name, you've probably already met it in three-dimensional Euclidean space under a different name. Metric tensor is very simply the dot product for that space. The dot product is kind of like this machine where you input two vectors and the machine outputs just a real number. What's really cool about the dot product, or metric tensor, is when you feed it the same vector twice, you get its length squared as the number output. Take the square root of this, you then get its length. It turns out that the dot product fundamentally depends upon the space that you're in. The dot product on the surface of a sphere is fundamentally different to the dot product on the surface of a flat piece of paper. In four-dimensional flat space-time, which is the arena of special relativity, the metric tensor is a four-component matrix of this form, where mu now takes on the values of 1, 2, 3, and 4. It takes in a thing called a 4 vector, which could be, for example, the difference between 2 points in space-time, and tells us in a meaningful way what the distance between them is. Slightly confusingly, length in space-time can be positive or negative. Here, these negative lengths just mean that the distance in space-time is a temporal distance rather than a spatial one. This is the metric tensor, or the dot product, of flat space-time where there's no gravity at all. A Schwarzschild black hole is essentially a very particular solution or kind of metric tensor, which describes the geometry of space-time outside of an infinitely dense source of mass. RS is known as the Schwarzschild radius and is essentially the black hole's event horizon. For the purposes of this video, we only really need to worry about the first two components of this metric, known as the time and radial components. From now on, mu will only take on the values of 1 and 2. Something very interesting happens to these components at the Schwarzschild radius, i.e. r is equal to rs. The radial component, 1 over 1 minus rs over r, actually blows up to infinity, and the time component, 1 minus rs over r, goes to 0. As some intuition as to what this actually means, consider the following two-component vector. The first component, 1, represents the distance in time between the two events, and could be, for example, 1 second. The second component represents the difference in radius away from the black hole's center. In this case, because it's 0, we're considering two events that are happening at the same radius that only differ by a small time delay. Now, consider two events that are happening at the same time, but at different radiuses. The difference between the two events is represented instead by this vector. Let's now use the first two parts of the flat space-time metric, the metric where there's no gravity at all, to figure out what the distance in space-time between these two vectors are. For the separation in space, we do the dot product, and the answer we get is +1. For the separation in time, we do the dot product, and the answer that we get is -1. Don't worry that the time length is negative. If you like, just imagine that the negative sign isn't there for now, and just think of it as a 1 second duration. Now, consider the case where this exact same situation is happening near the horizon of the black hole. We need to use the metric tensor at the point r is equal to rs. When we do this, and we use the Schwarzschild metric, the time separation dot product gives us 0, and the spatial separation dot product gives us infinity. So what do these equations mean physically? Well, what was a separation in time of 1 second when there was no gravity present at the horizon is now a separation in time of 0 seconds. Time at the horizon, from our perspective, does not appear to have passed at all. Similarly, what was a length of 1, say 1 meter, where there was no gravity present, is now infinitely long. As we'll see really shortly, this is totally the reason why black holes are black. First, we need to get our head around something very strange. If time doesn't appear to pass at the horizon, then how can we ever see anything fall into the black hole? Shouldn't we see everything that ever fell into it just stuck there, piled up at the horizon? Surely this should make the horizon, and hence the black hole, not black. See why this isn't the case, and why we really do see nothing. We need to remember a fact about light. The energy of a light ray is related to the amount of time that it takes to complete one oscillation. And the longer that it takes to complete this oscillation, the less energy that light ray has. Now what you have to fundamentally remember is that it's the energy of this light ray which is alerting us of its presence. Light has to physically interact with us, and that's why it's visible. So what we found is that somebody who emits a light ray at the horizon, and say it takes 1 second for this light ray to complete one oscillation, it will take an infinite amount of time to complete one oscillation from our perspective. Therefore, this light that comes towards us has 0 energy, and hence it can never interact with us. Well, what do we call light that has no energy? Black. There we have it. This is the real reason why black holes are black. It's a phenomenon known as gravitational redshift. Anything from the horizon, from our perspective, gets infinitely redshifted and therefore becomes black. Thank you very much for watching. I hope you enjoyed the video.